In a perfect world, we'd probably have a single measurement device that measures everything. In the world we live in, though, there are always trade-offs among a range of parameters, and one has to choose the optimal solution. If you need to measure power or energy of your laser beam, the choice of sensor will depend on many factors, including the power or energy level, beam diameter, wavelength, whether the beam is continuous or pulsed, and more. So how do you choose? The Ophir Sensor Finder, a tool available for use on our website and also for download, does most of the thinking for you. It asks you for information about the measurement you need to do, and then gives you a list of suitable sensors that can do it. To get to the Sensor Finder, you can click on the direct link on the main page of the Ophir website, and also the main page of the Ophir Photonics Group website. If you want, you can then download it to your own PC by clicking here. This is the main screen. In step 1, we set up the basic measurement type. And then in step 2, we enter the laser parameters. As a sanity check, the sensor finder will then show us the calculated power density, energy density, and average power based on the parameters we entered. If something here doesn't make sense, we might go back and check. For example, maybe we used the wrong units. Then we click on the Find Sensor button, and the sensor finder will give us a list of sensors that fit the parameters of our laser. Let's walk through a few examples to see how this works. Example 1. We'll choose CW, flat top, circular beam, 5 millimeter beam diameter, 532 nanometers, 10 watts power. Here we see the power density, which the sensor finder calculates by simply dividing the power by the spot area. If we select a Gaussian beam profile instead of flat top, note the change here. In a Gaussian beam, the local power density at the center of the beam is approximately double the overall average power density and needs to be taken into account in terms of damage threshold. This is expressed as peak power density as displayed here. Note that if we don't specifically enter a minimum power, the sensor finder will assume the minimum is half of the maximum. This could be important if you're working near the lower limit of some sensors and don't want them to be incorrectly left out of the list of proposed solutions. Click on Find Sensor, and the output is a list of potential sensors, generally in increasing order of price, so the first few are usually the ones to consider. Here at the top, we're shown a summary of the parameters we entered, again as a sanity check. The percent of damage threshold tells us how close we are to the maximum power or energy density that the sensor can handle without damage. In general, we recommend that as far as possible, you keep a safety margin in place by choosing a sensor that, in your measurement conditions, will not be at more than 50% of its damage threshold. In this case, as you see, all sensors in the list are below 10% of the damage threshold, so damage won't be a concern in this case. If there are any notes regarding a particular sensor, such as special features or limitations, those will be referenced in the Notes column. If you want to see any details about a given sensor, the sensor's specs for example, clicking on the link for any sensor takes you to the particular sensor's information page on the site. Example 2. Now let's see what happens when the laser parameters are problematic. Let's use a 1 millimeter spot diameter and 1000 watts average power. Note the extreme power density. Sensor Finder not only tells you that no solution is available, it also suggests why. In this case, it could be that the spot size we entered actually referred to a focal spot, for example. And all we need to do is measure at a location where the beam is not focused. Even a few millimeters outside the focal plane, the defocused spot diameter might be 7 millimeters, for example, and then choosing a sensor becomes easy. Example 3. Now let's consider a rectangular beam. When we select rectangular in step 1, we're prompted to enter 2 dimensions in step 2. Let's say 10 millimeters by 15 millimeters. We'll use 1064 nanometers, 120 watts. We're offered a range of sensors, all of which use fan cooling to handle the 120 watts of average power. Let's say, though, that we only need to measure intermittently, taking a reading for only a few seconds at a time. Since the actual average power will be low, maybe we won't need a fan-cooled sensor. We go to the optional for best search area in step 2 and enter the expected exposure time, let's say 1 minute. Now the solutions include a range of sensors that are designed to handle higher powers intermittently without needing fan cooling. The 5150A type of sensor, for example, can measure 50 watts continuously and up to 150 watts intermittently. Example 4. Now let's find a sensor for measuring energy per pulse. In step 1, we now select energy and power instead of power only. 4 millimeters, 1064 nanometers, 350 millijoules. Note that sometimes we know the average power but not actually the energy. Sensor Finder enables us to work that way if we need to, since of course energy, repetition rate, and average power are all mathematically related. 20 Hertz. Note that if you're working in single shot mode with at least 4 or 5 seconds between each fired pulse, single shot energy would be selected by entering single here in the max rep rate field. 100 nanoseconds pulse width. The range of proposed sensors will include various types, sometimes proposing an energy sensor together with a beam splitter accessory in order to handle high energy densities. If you still need help, for example if the sensor finder doesn't manage to find you a solution, you can save your search data and send it to us. Or just contact us through your local Ophir representative or directly, and we'll be happy to help you with your application.